It is a pleasure to introduce our next speaker, Professor Mykola Nikitchenko from Taras Shevchenko National University of Kiev. The title of the talk is Program Algebras and Logics of Nominative Data.
I came from informatics, so I will discuss in this talk algebras and logic in applied domain, different domains. So we can see the role of algebra and logic, main aspects of applied model and program algebras, classes of nominative data, program specification algebras, and conclusions. So now we see that a lot of domains are used by artificial intelligence. And this active use of artificial intelligence started with large language models, which recently evolved to systems explicitly designed for reasoning tasks, large reasoning models, such as OpenAI, DeepSeek, Sonnet Thinking, Gemini, Thinking, etc. And these models are new artifacts characterized by their thinking mechanism. They have demonstrated promising results in various domains. But there are problems. What problems? First of all, we see a lot of subject domain. In such domains, we have different methods of reasoning. And so what we have now have some limitation of large reasoning models. What to do? To answer this question, it is necessary to carefully study the mathematical foundations of reasoning systems, and this primarily means the construction and study of logic, both general and specialized. But what is logic based on? The main idea is, of course, that logic is based on algebra, and so we should consider construction and investigation on various types of algebras and logics based on such algebras. In particular, program algebras and logics were considered in this talk. So, as we can see, a variety of applied domain and their features, we should concentrate on some of them and make some models. We will consider here such aspects as intentionality, nominativity, compositionality, and partiality. What is intentionality? It is opposite of extensionality. So intentionality specifies properties, say behavioral properties of subject domain, and is complementary to their extensional characteristics. What is important for us is intentional characteristics can be classified according to the following levels of activity: pure activity, becoming activity, determinate activity, real and actual activity. It goes maybe from philosophy, where philosophers distinguish such types of levels. What does it mean? The pure level means no activity. Becoming level means that transitions are allowed. The determinate level is related to the qualities of things. The real level is based on properties of things, and actual level is associated with actions in the domain. So we have 5 levels at least. At each of the level, we can construct many algebras and many logics. Then next, nominativity. The model of states of the subject domains can be specified by nominative data. What does it mean? It means that we use names, variables, and values. They can be hierarchical. And in this case, we obtain hierarchical nominative data. Such data can represent various data structures used in informatics, artificial intelligence, computer science. Compositionality. The construction or program construction can be formalized by such operators, which are called compositions. So to each level, we identify compositions, and thus we will obtain algebras. In general, when we use nominativity and compositionality, we obtain composition nominative algebras. Next is partiality. In conventional algebras and logic, functions and predicates are considered as total mappings. But in applications, we often encounter situations with partiality. And this requires constructing algebras and logic, of course, with partiality both in data and functions and predicate. So let me give a small example about levels of intentionality. Let us assume that a volunteer asks a refugee about her needs. Then the situation develops as follows. First, the refugee asks the volunteer to provide her with a phone. The volunteer analyzes the refugee needs and the availability of money with phones, the work of the providers in that area, and based on this information, he ordered a phone. When he received the parcel in the phone, he checks whether it is the phone he ordered. Then, together with the woman, they set up the phone. The refugee calls her relatives and tells them the news. So we have such levels. And this, as I already told, we may call them pure level, becoming determines real and actual levels. Pure level, no activity. Becoming level, transition. Determinate level, acceptance activity. So if I receive a phone, I can accept or reject it. Real level, acceptance, but associated on the properties of the phone. Properties, we can change settings. And actual levels we can use, so we can make actions, activity, and go outside the scene and make a call. For example, the organizers of the conference. So now we should construct algebras and then logic related to such levels. Pure level, degraded algebra, no operations. Becoming level, transitions system, determinate Boolean algebra and propositional logic. Real, predicate algebra and logic, and actual model and program algebras and logic, and many other logics. Here we concentrate on program logics. One example, this is a program for calculating a function x power n by exponentially by squaring algorithm. So what we see in this program, we see assignment operators, we see if operators, sequential execution operators, while operators, and of course variables r, n, x. So these are components of this program, and we should formalize this program. We will use so-called denotational semantic. We will represent semantic of program as a function. But what are states of the variables? States are simply assignment in logic. This is a function from variables, from names to values. Because we can see the partial function, we use this notation V before A, upper index V. And thus we have that states are such functions, such partial functions. For example, we can write for this program such kind of stations. And so D will represent the state of this program. I will speak about execution, evaluation of the program of some data. We obtained very simple data algebra, having integer with traditional operation, addition, subtraction, multiplication, division. So we have Boolean carrier with disjunction, conjunction, negation, and we have states, and programs are defined over states, and there are such operations as naming, denaming, identity, overriding, and so on. Thus, we have arithmetical expression, Boolean expression, and statement operators, and semantics is represented, you can see, by function from state to A. State is a nominative data. Thus, we have partial function which represent component of this program, and programs or statesmen are function from state to state, partial function. We have operators. Here we call this composition. So we have assignment composition, sequential composition, if composition, loop, while, iteration, if you like. And thus we obtain an algebra. It has three carriers: predicates, functions, program, and operations we already considered: disjunction, negation, superposition, substitution, if you like, denomination, assignment, sequential execution, if and while, and plus symbols for basic functions. That algebra can be called program algebra, but we would like to investigate our programs. And we should introduce composition which, given a program, can specify its properties, and such algebra we will call program specification algebra. We will use here Floyd-Hoare composition when given a program, given precondition and postcondition. It yields a predicate, and this predicate expresses properties of a program. So we have three levels: pure level of predicate. Here we can introduce denomination operations, existential quantifiers. Then we add ordinary functions. And to relate these predicates or functions within themselves, we should need superposition compositions to predicate auto functions. And we have programs have operation like assignment, if, while, and so on. So we have, in this case, three carrier algebra and operations on these carriers. And our question is to study this algebra and to construct logic that permit to prove properties of programs or make verification of programs, for example. There are some logics. The most widely used is so-called Hoare logic or Floyd-Hoare logic for deterministic case, and multimodal logics for non-deterministic programs. These are quite traditional rules. I will not discuss them, and let me go on. So as you can see, we should describe algebra of data, then we should describe functions formalize activities. We obtain many sorted algebra, and based on this algebra, we construct logic. While constructing these algebras, we should include intentional features, as I told, say, levels of activity. And we can speak about intentionalized data. It means that we should describe some properties, not only extensional definitions, but intentional, some properties. Usually it is not formalized very strongly, but intuitively we can see what does it mean by intentionality of data. First, we start with data as a black box, so nothing in node, then as a firebox. So here we will have pure level, nothing in node about data, nothing of activity. Here we have transition, automaton, semi-automaton, and so on. Then we can combine at the determinate level when we know qualities and we don't know, say, essence, and thus we obtain level of nominative data, or if you like partial case, presets. So when we have white elements, we obtain series of sets. When we have partly black boxes, we obtain presets, hierarchical presets. When we consider name data or nominative data, we obtain again hierarchy of nominative data. So there are examples of such nominative data. Say flat data, we have no hierarchy. Hierarchical data, the name X have again as a value nominative data. Names can be complex or simple, values the same can be complex or simple. And in this case, we obtain the cube of nominative data type. Say this is the simplest case, simple name, simple data, direct naming. We can have indirect naming. What does it mean? Indirect naming that the value is again a name, which indicates on the other value. Say, if you have an array and reference to the element of array, like a name of array, and square brackets I plus 1, I plus 1 plus 1 in an expression, you should evaluate the name of this expression, obtain an index, and then you can refer to the elements indicated in the program by this a I plus 1. And the question is to study, to construct, to investigate this data and algebras based on this data. So we can consider nominative data as a universal or logical data structure which can present more model various data structure used in computer science, artificial intelligence, and so on. So we consider classes like simple names, simple values, or complex name and complex values. There are some formal definitions. Say simple names, simple values with basic elements A are simply functions from V partial function to the values. And the problem usually arises when we consider complex names, complex name as a sequence of names. The problem is how to work with data which has complex names. So we define various operations for such case, and of course many restrictions to work with such complex nominative data. There are some trivial lemmas, and what we can do in this case, we can introduce equivalence relation based on associative naming and denaming. What does it mean, associative naming? It means that, like in semi-groups, that we simply do not take brackets into consideration, and this, of course, greatly simplifies the investigation of nominative data with complex names and complex values. So we can introduce these equivalence relations and construct Gaussian sets and prove that there are equivalents. In other words, it means that it not necessarily consider 4 cases. We can introduce while case which is related to simple name or complex values, or complex names but simple values because they are isomorphic. We introduce operations like deleting, updating, denomination operations for such data algebra, and thus we construct special algebra of hierarchical nominative data. Then we investigate specification algebra. What does it mean, specification algebra? It means that we should study predicates over hierarchical nominative data, functions over such data, and program of such data. We should redefine composition. For example, here it is written exists X but X should be considered as a sequence of names, as a complex name. So from specification algebra, we go to specification logic of a hierarchical nominative data. What we should do to define such a logic? We define classes of algebra, which form semantic base, logic language based on logic signature, class of interpretations. Interpretation specifies objects under acceptance, consequence relation, and inference relation based on some calculus. What is the problem? There are, let me say, the following problem. First, we have rather complicated composition. Second, we have partial predicates. And for partial predicates, we don't have nice axiomatics and nice consequence relations. And of course, the inference relation will be rather complicated. We introduce so-called irrefutability consequence of gamma under undefined condition U in interpretation J. What does it mean, this consequence relation? Let me demonstrate here. So in traditional consequence relation, in premises are valid, then a consequence should be valid, but we should take here into account that there are cases when premises, so to say, are undefined, and so we should construct special relation. Formal definition is this, and then we should study this consequence relation, in this case in property, and based on these properties, we construct inference systems for such logic. Let me only stop on this. So this is disjunction, but now disjunction can have three possibilities. It can be true, here, for example. It can be false, and it can be undefined. So if disjunction is undefined, we would like to prove this as a consequence. There are three cases in the second calculus. Both arguments are undefined, or one is undefined, the other is false. And having these three cases, we can make a conclusion that the disjunction can be undefined. There's one more rather complicated composition, which may be called complement, to define as domain of predicate. And then we again consider rules for the complement. So if we would like to prove that complement is true, then it means that phi should be undefined, because complement specifies undefined domain. Here are a lot of rules for superpositions or substitution, if you like. As a rule, they are distributive. It's rather easy, but still we should take into consideration undefined domain, and there are some restrictions. Of course, for quantifiers, we have again specified three rules, put restrictions. Then we construct new system. Again, because we speak about partial predicates, we cannot use classical system. We should generalize this for partial case, so there appear some additions, some hot triples here and in while appear. We investigate this inference systems or axiomatic systems and prove its correctness. So, conclusion. First, we say that hierarchical nominative data can adequately represent data structures used for program development. Intentionality permits to define levels of data considerations and data algebras on the basis of constructed nominative data and program algebras. program logic can be constructed and verification methods can be proposed. Constructed algebra logic take into account such features as intentionality, nominativity, compositionality, and partiality. Thank you very much for your attention.